Great. Okay, so a very warm welcome to everyone. I hope the weather's not too wild where you are. We were talking about that before. I'm actually heading down to Birmingham University on Monday for a two-day meeting, so I know that's not too far from where many of you are. I'm hoping the weather will have calmed down a bit by then. But delighted to be able to join you on Zoom. So I've called this Listening to Einstein's Universe, the Dawn and Exciting Future of Gravitational Wave Astronomy. And as we were just talking about, much of it will be to do with LIGO. I'm wearing the sweatshirt proudly. Stands for Laser Interferometer Gravitational Wave Observatory. So over the course of my talk, I'll hopefully explain what LIGO is all about, how it works, what we've been able to detect so far, and what lies ahead in the future. It's a new branch of astronomy, you might say. And although it was about 100 years in the making, because it goes back to the time of Einstein, as we'll briefly begin by looking at, it's very much at the cutting edge of what's being discovered at the moment. So I'm delighted to share all that with you. Let me just say a little bit more about me. So my kind of official title as an astronomer is Professor of Gravitational Astrophysics and Cosmology. But I'm also now Vice Principal of Glasgow University. So that does take away quite a lot of time that I used to devote to LIGO work. I'm still quite active in the research itself, but I used to be one of the division heads of LIGO, the whole collaboration. There's about 1,700 people worldwide. So that was a big demand in my time, just, responding to questions and keeping everybody happy as best I could within our division. But I'm no longer in that role, but I am still strongly involved in some of our analysis work in the part of LIGO that we refer to as cosmology. So that's all about trying to understand the big scale properties of the universe, not this particular galaxy or that particular star, but the big picture, answering questions like how big is the universe, how did it begin, and why is it expanding? So we've been asking those kind of questions for nigh on a century, because about 100 years ago, Edwin Hubble, after whom the Hubble Space Telescope is named, first discovered that our universe is expanding. And that decades later, when I kind of came along, I began working in cosmology in the late 1980s and 1990s. There were still a lot of questions about that expansion that we didn't have answers to. Specifically, we hadn't really measured very well how fast the universe is expanding. So one of the things that got me interested in gravitational wave astronomy was the possibility that we might be able to answer questions like that using gravitational wave data. So I'll try and talk a bit about that towards the end, after I've kind of set the scene more generally. And setting the scene more generally is really just to give you an introduction to gravitational wave astronomy itself. What's it all about? What are gravitational waves? What kind of objects produce them? And how can we detect them? So it's going to be things like black holes and neutron stars, examples of really quite extreme cosmic objects that are not like your even everyday common or garden stars like the sun, but much denser and much more extreme objects where the gravity is much stronger. So that's what lies ahead. We'll try and cover all of that in about 45 minutes or so that there's a good time for questions and discussion at the end. So the LIGO scientific collaboration, let me say a bit more about what that is. I've mentioned already that it's well over 1,000 scientists. I think we're about 1,700 now. Many different institutions across the world, a lot of them in the US, but quite a lot in Europe as well, even some in Australasia and in Asia. We don't have anyone in Africa yet, but we're working on that too. We want this to be a global collaboration, not just because the more scientists you have working on a problem, usually the better you can do, but also because the detectors themselves will work more effectively if they're spread all around the world. So over these next few slides, we'll talk a bit about how the detectors operate, but you should bear in mind that we actually have two LIGO detectors. There's one in Livingston, Louisiana, and one in Washington State, Hanford, Washington. And this was not buy one, get one free. They are expensive. At the time, were the most expensive and most ambitious project that the National Science Foundation in the US had ever undertaken. But nonetheless, it's important to have more than one detector for reasons that we'll discuss a little bit later. So what are they? So LIGO is a laser interferometer gravitational wave observatory, as I said before. So it uses laser light to try and sense gravitational waves coming from far out in the cosmos. And even LIGO itself isn't the full story now, because there are two other global collaborations called Virgo and CAGRA, involving multiple countries, although CAGRA is mainly Japan, but there's a few other countries involved as well. And that emphasizes that this really is science that we try to do all around the world, involving scientists and engineers from a wide range of countries and a wide range of different fields. So the diagram you can see on the left is a kind of infographic to just try and give the big picture as to how the laser interferometry works. What we do is we send laser beams along two arms perpendicular to each other at right angles to each other. And the LIGO detectors have arms which are 4 kilometers long. And the laser light gets bounced back and forth along those two arms. And what we're looking for is the effect of a passing gravitational wave changing the pattern of the laser light when we recombine it again. So the next few slides will go into some more detail about how that all works. But before we even get there, I just wanted to begin by taking a little bit of a step back to see where all these ideas about gravitational waves actually came from. And you can really trace it all back to Einstein. So Einstein's been a big influence on my research career. A lot of the work that I've done is related to theories and ideas that Einstein first put forward in the early 20th century. And in 1905, he published his special theory of relativity, which is all about how space and time are affected, how we perceive space and time to be affected when you're traveling close to the speed of light. But then 10 years later, he published his theory of gravity that we call general relativity. So even Einstein took 10 years to make the jump from his special theory to his general theory. And what the general theory of relativity is really trying to say is that gravity is not the force that we learn about from Newton at high school, you know, the laws of Newton that he developed hundreds of years ago to tell us how bodies would respond to accelerations and would experience a gravitational force. But what Einstein thinks about gravity as instead is a bending, a curving of space and time themselves. So to come up with this picture, he had to introduce a lot of quite complicated maths, and don't worry, I'm not going to go into any of that detail in my talk tonight, but some of that maths is sort of captured on this statue here. I really like this statue. It's in Washington, and I sort of go and see it anytime I can if I'm visiting Washington, DC. It's at the National Academy of Sciences, and the sort of weird-looking equation at the top is Einstein's equations of general relativity, his theory of gravity. So again, don't worry, we're not going to get bogged down in all the maths of the equations, but there is one equation I want to mention. It's the bottom one, and if you can just about make that out on the screen, it says E equals mc squared, and you've probably all heard of that one. It's a sort of famous one where Einstein talked about the energy associated with a certain amount of mass. And the c in the equation is the speed of light, 300,000 kilometers per second. So when you square that, you've got a really big number. So what that's telling us is even a small amount of mass contains a vast amount of energy. And that's important for what I'm going to talk about in terms of how we can detect gravitational waves and what they maybe tell us about the universe. So this idea about space and time in special relativity and then gravity in general relativity, you know, there's a degree of truth in saying that they've made Einstein probably one of the most famous scientists of all time. And in fact, in 1999, Time magazine voted him not just the most famous scientist of the 20th century, but the person of the 20th century, because of the ways in which his ideas about space and time would influence our lives and would develop a lot of the technology that we now kind of take for granted. And I should note in passing that was the editorial board's decision of Time magazine. There was a public vote as well, and the public voted for Elvis Presley. So you can decide for yourself who got that one right. Whether Elvis is more important than Einstein, well, I like them both, so I'm not going to take sides there. But Einstein is definitely a kind of scientific hero of mine in terms of the really groundbreaking ideas that he came up with about the nature of space and time. And he did a lot of that when he was much younger than the kind of white-haired, you know, old mad scientist that you see on the Time magazine cover. He did a lot of that work when he was just in his 20s and 30s. So, I'm well past my prime in those terms. It's kind of downhill all the way for me. But Einstein did a lot of his really, really great work when he was quite a relatively young man. So what does it all mean? Well, I've mentioned already that we think about gravity in Einstein's theory as a bending of space and time. And often a good way to represent that, you might well have seen this before, is to think of like a rubber sheet, like a trampoline. And if you drop a massive body onto a trampoline, then the trampoline is going to deform. It's going to change its shape, a bit like it's been shown in the cartoon on the right here. So what we've got is the Earth bending the space-time that the Earth is sitting in. And, that's just a metaphor. It's grossly oversimplified. But nonetheless, it sort of helps me at least to visualize what's going on. And it gives us a sense of why gravity acts the way it does. Because instead of Newton explaining the moon orbiting the Earth by there being a force of gravity between the moon and the Earth, what Einstein would say is that the moon orbits the Earth because it's following the curve of the space-time that the Earth is sitting in. And you can kind of see that, in metaphor form, as that sort of stretched sheet of rubber like a giant trampoline. And there's another neat way to sum all of that up, which is a phrase due to John Wheeler, a scientist who was around a wee bit after Einstein. And John Wheeler said that you can describe Einstein's theory of gravity like this, that space-time tells matter how to move, and matter tells space-time how to curve. So the presence of matter, just like the Earth in the picture, is curving space-time, and then that will determine how other bits of matter, or actually also light or gravity waves, will follow those curves, will follow that curve path. So the moon orbits the Earth because it's essentially just following the curve of the well, the gravity well that the Earth is embedded in. So that's just in a matter of a few minutes, my attempt to try and give you a sense of what Einstein's theory of gravity is all about. And of course, I'm only scratching the surface, but I hope that that's helpful just to give us a wee bit of context for what's about to follow. But you're probably all familiar with the idea of electromagnetic waves. The optical light that we see with our telescopes and we see with our eyes is just one part of that electromagnetic spectrum. It goes all the way from radio to gamma rays and X-rays. But gravitational waves are a different type of radiation altogether. They're not like outside the electromagnetic spectrum. They're a completely different spectrum of radiation altogether. And the best way to think about where they're coming from is maybe to go back to that trampoline analogy again. Again, it's just an analogy, but it's quite helpful, I think. So if you have a stretched sheet of rubber, you drop a heavy body on it, well, the rubber sheet's going to wobble. And essentially, that's what we can think of gravitational waves are. They're the wobbles or ripples in space-time itself caused by accelerating massive bodies. So I hope my animation is working. Again, I've not got too many animations in the top, but I've got some. So hopefully that's coming through at your end. And what it's showing is just in cartoon form, two stars orbiting closely around each other. And what that's sending out is these ripples in space-time. Think of a bit like ripples in a pond when you drop a stone into a pond. That's essentially what our gravitational waves are. They're ripples in space and time caused by changing gravitational fields. Now, that means that, strictly speaking, if I wave my fist, hopefully you can see me do that with my virtual backdrop, then I'm producing gravitational waves because my hand has got mass and the distribution of that mass is changing because I'm wiggling my hand about. But the amount of gravitational waves that produces, the strength of the waves is unimaginably tiny because, well, my hand only, weighs a fraction of a kilogram and I'm not waving it very fast. So Einstein's equations tell us if you want to produce gravitational waves that we have any hope of measuring, then what you need is really massive, dense bodies like neutron stars or black holes, where the mass is concentrated into an incredibly small volume. In the case of a black hole, the volume is so small that even light can't escape from it. That's why we call them black holes. And what you've got to have is that distribution of mass changing very, very rapidly, basically close to the speed of light. That's the kind of conditions that might give you these gravitational waves strong enough that you might detect them. And that's basically what the LIGO project was trying to do, to detect these space-time ripples predicted by Einstein's theory of gravity back in 1915, but not observed until 100 years later. So why did it take us so long? Well, for a long time, we weren't actually sure if these gravitational waves truly existed or if they were a kind of mathematical artifact of the equations. But from about the 1950s and 60s onwards, there was a growing belief within the scientific community that they were real, but they were just incredibly weak, incredibly faint. And it's really related to how weak gravity is compared with the other fundamental interactions of nature. You might have heard of them. There's the strong and weak nuclear force, and there's electromagnetism itself that we mentioned a moment ago. So gravity, well, in Newton's description of gravity, the strength of the gravitational force, or the gravitational field, is described by big G. It's a number that we call Newton's constant of gravity, and it's a very small number in the sort of usual SI units that we measure things in science. It's 6.673 times 10 to the minus 11 in those kind of standard units. And what Einstein's equations tell us is that the strength of the gravitational waves, these ripples that we're searching for, that strength is proportional to that number, big G, but divided by the speed of light to the power 4, G over C to the power 4. So 6 times 10 to the minus 11 divided by 3 times 10 to the 8, actually 3 times 10 to the 11 because I've got to use meters rather than, no, but 3 times, we'll stick with 3 times 10 to the 8 in meters. But the point is, when you raise it to the power 4, then it's going to be really tiny. So basically, it says that if we want to produce gravitational waves that we can measure, you can't like build a bit of equipment in the lab to do it. You can't wave your fist to do it. You've really got to use the universe itself as your sort of cosmic laboratory and look for examples of extreme gravity where things are changing so fast that it produces ripples that we might hope to measure. And even then it's a challenge, because those space-time ripples, even if they're being produced out there in the universe, as they spread out through the universe, they're going to be observed to be weaker by the time they arrive at us. So bottom line, the kind of signals that we're looking for are disturbances in space-time equivalent to movements of about 1,000th the size of a proton. That's the subatomic particle in the heart of a nucleus of an atom. Or if you want to put it in slightly more everyday terms, if you take one of the hairs on your head, you're talking about a millionth the width of one of those hairs. So by the time these ripples reach the Earth, to detect disturbances as small as that is an incredible, not just scientific challenge, but an engineering challenge to build a detector that's sensitive enough to pick those signals up. But that's what LIGO does. That's what the LIGO detectors and the other detectors that I'll mention later in our network around the world, that's what they are capable of doing. So I mentioned before that there was one in Louisiana, one in Hanford, Washington. That's the top right and bottom left, respectively. There are 3,000 kilometers apart on either side of the continental US, and they've got this L shape, like I said before. So laser beams are sent along those two arms at right angles to each other. And I've got a wee cartoon in this slide to sort of give a sense of what goes on inside the detector. Remember, we're trying to detect a millionth the width of a human hair. That's equivalent to about measuring the width of a hair compared with the distance from us to Alpha Centauri, a change that small. So the way it works, this animation will run a couple of times, is that we take the laser beam, we split it into two perpendicular beams. One goes along one arm, one goes along the other. And then we bounce the laser beam off mirrors, we recombine the laser beams. And if a gravitational wave passes by, it will stretch and squeeze the space-time that the LIGO detectors are sitting in. And that's sort of represented a wee bit by the cartoon on the right-hand side. You can see the stretching and squeezing. It's hugely exaggerated. But what happens is when the length of one arm gets a little bit longer, the other arm gets shorter, and then vice versa. That's the pattern that we would expect, according to Einstein's theory, when a gravitational wave passes by. And the effect that will have on the laser light is that it will change the way that the two beams interfere with each other. So you can get destructive interference, where the two beams basically cancel out because the peaks of one wave cancel with the troughs of another. Or you can have constructive interference where they add together. And if the arm lengths are changed by a passing gravitational wave, that will alter the interference pattern. So that's why we call it a laser interferometer. And therefore, we can look for changes in the interference pattern to help give the signal that a gravitational wave has passed by. Well, that's the theory, but to do it in practice is a real challenge because these signals are so incredibly small. So what helps us is that we think we understand what the pattern of how the interference changes ought to look like. So I don't know how well you can see the animation in the left-hand corner. It's a wee bit dark, but what you've got there is two black holes, two regions of space-time where the gravity is distorting space-time so much that even light can't escape, and they're orbiting around each other. This is just a simulation, and it's showing the two black holes getting closer together. As they do, as they spiral in towards each other, they give off these ripples, these gravitational waves, and they get stronger and stronger the closer the black holes get together. That's what Einstein predicts. And that's reflected in the graph above. I know maybe graphs aren't everybody's cup of tea, but this one hopefully isn't too complicated to describe. What you see here is as time elapses, it's showing how much distortion in gravitational waves is being produced. And what we see is that the amount of the distortion, that's the vertical extent, that's increasing. We call that the amplitude of the gravitational wave. And then the peaks and troughs, they're getting closer together. That's the frequency of the gravitational wave. So this distinctive pattern is known as a chirp, because what we're seeing is a rising frequency, they're bunching up, and also getting louder because the amplitude is increasing. So this is really what Albert Einstein's theory of gravity predicts that we would see if a gravitational wave from two colliding black holes were to pass by. So we knew kind of what we were looking for, or maybe more appropriately, one could say listening for. Because the frequencies of gravitational waves that the LIGO detectors are sensitive to happen to coincide with frequencies that the human ear can hear. So gravitational waves are not sound waves, but we can show them in a picture like on the screen, or we can actually represent them as sound waves. You know, the name chirp kind of almost suggests that. The chirping pattern is a bit like, you know, the sound that a bird would make, going, you know, well, that's not a very good impersonation of a bird, but it's, you know, rising in frequency, rising in pitch, and rising in amplitude and getting louder. So that's why I called my talk Listening to Einstein's Universe, because in a sense, we can think of us searching for these gravitational wave signals by listening for these patterns of chirps. And that's, I think, quite useful, again, as an analogy, because it also gives us a real sense of what the challenge here is. So this is a photo I got from a colleague in the States. It just shows a lunchroom in a college where he'd gone to give a talk. And I imagine it was pretty noisy in there. You know, lots of conversations going on and probably hard to hear yourself think. And even people talking to their neighbour might struggle to hear what each other is saying. But if you've got a good idea of what you think the other person is saying, then often it's relatively easy to work it out. And in fact, quite often in public outreach or schools outreach, we'll do a little game, a bit like this. We call it Black Hole Hunters, where, well, you know, one group of students get to sort of say a message, you know, they can make it up themselves, you know, we can do it that way. Or another group has to try and listen for that message. And the third group, well, they have the most fun part because they just get to make as much noise as they can. And the point is, it's very hard for the people trying to listen for the message to hear the message over the background noise, but you can improve it if you either reduce the background noise or if you give the people listening for the message an idea of what the message is supposed to be. And, you know, we've done sort of tests with this and find that, yes, the human ear is actually pretty good at that, at picking out a message, picking out words from a noisy background. So that's very much like what we're trying to do with our gravitational wave detector. But of course, what we also wanted to do is reduce the background noise. So that was where we were by 2010. We'd been operating the gravitational wave detectors for a few years, but the background noise was too high. It was like being at a particularly noisy party where you can't hear yourself think. So what we tried to do was to improve the way in which the detectors were made sensitive to the signal by reducing their susceptibility to background noise. So the mirrors that we talked about bouncing the laser beams off, those are actually suspended by in the latest version of LIGO, not steel wires like they were before, but silica fibers of glass fibers. And some of my colleagues in Glasgow were heavily involved in the research and development of this new suspension system, this new way of suspending the mirrors, and then actually installing these upgraded suspension fibers in the LIGO, turning LIGO into advanced LIGO. And the point is, these silica fibers are less likely to wobble in the presence of background disturbance. So what you're doing is you're isolating the mirrors more effectively from any background seismic noise or other sources of local disturbance, things that have nothing to do with gravitational waves from out there in the universe, but just have everything to do with the ground shaking down here on Earth. So the initial LIGO detectors weren't as good at doing that, at isolating themselves from the local background disturbances. Advanced LIGO was better. And our hope was that that would be a real game changer, that it would allow us to detect signals that previously were just swamped by the background noise. So by 2015, we were ready to begin operation of advanced LIGO. The two detectors had been upgraded in this way. The UK played quite a major role in that. We were very proud of the opportunity we had to really make a difference in how the detectors were operating. And sure enough, well, let me just let you hear the sound first. I'll just pause it. There we are. I'll pause it so that you can now see the images as well. Hopefully the sound was coming through. What you were hearing there was repeated on a loop. The data that we got in September 14th, 2015, you probably can't see it, but it's actually on my sweatshirt as well. This was our first detection of gravitational waves. And it's turned into a sound wave. So first of all, you've got the pictures just like before. You've got those blue and orange wiggles. And then above them, just another way of representing essentially the same thing. It's called a periodogram or a spectrogram, where what we're doing is showing how, as time advances, the frequency increases. The frequency sweeps upward and the signal gets louder or brighter. But as I said, we're also representing it as a sound. So it's on a loop, so it's repeated multiple times. And I'll play it again, and you can sort of listen in for this. What we do is we first of all play it at the actual frequencies that were detected. And what you'll hear is a kind of a thud. It's not terribly exciting, but that's the sound, rendered as a sound associated with the gravitational wave signals. But then what I do is I shift it up to higher frequencies. Think of it a little bit like what we often do with astronomical images, of presenting them in false color so that you bring out detail that's easier to see. Well, this time it's to bring out detail that's easier to hear, because the human ear is a wee bit more able to hear the signal when it's shifted to higher frequencies. So you hear it as a little bit like that chirp sound that I was talking about before. So let me play that a few more times and give you a chance to hear that. So this happened on September 14th, 2015, all hugely exciting. And frankly, really from very early stages after we made this detection, we were pretty confident that it was the real deal, that it was a gravitational wave source. But then what we embarked upon was many months of painstaking work to try and check whether we'd got that right. Could it be anything else? Could it be some kind of local disturbance? Now, a large part of what helped to convince us was the similarity of the signals seen in the two LIGO detectors, even though they were 3,000 kilometers apart. If it was a local disturbance, it would really be very unlikely that it would look so similar just by chance, as another local disturbance at the same time, 3,000 kilometers away. It did only last for about a third of a second. Again, remember, I was playing it on a loop multiple times. So after about 5 months of very painstaking and careful analysis, we convinced ourselves that it was real and that the signal we had detected was coming from the collision of 2 black holes more than 1 billion light years away. So in February of 2016, we were able to announce that discovery. This is on the page from our website. So my role within the collaboration at that time was to lead a team that were preparing a lot of this news for that first detection. And we organised a press conference in February of 2016 where we announced that discovery. And well, in a little bit more detail, what we deduced from analysing the data that we had seen was the in-spiral, that just means, as the name suggests, the 2 black holes spiralling in towards each other, then the merger, and then what we call the ring down of the single black hole formed when the 2 black holes merged. So that's just a bit like space-time wobbling a little bit more as things settle down again after the black holes have collided. So the similarity of the 2 signals was a real calling card of this, and the pattern was as well. And in fact, I think my next slide is a little animation. It's narrated by one of my colleagues in LIGO, Laura Nuttall from the Institute of Cosmology and Gravitation in Portsmouth. So let me just share that with you. And it's just about a minute long, and it says a little bit about how we learn information about the black holes from analysing the shape of the gravitational wave data.
On the 14th of September 2015, one of these tiny gravitational wave signals was detected by LIGO. By comparing the signal to the predicted signal, scientists are able to find out more about the origin of the gravitational waves. To determine the mass of the black holes and their distance, we can compare with theoretical models. The parameters of the model are adjusted until the predicted signal matches up to the data. The closer the black holes, the larger the amplitude of the detected signal. The mass of the black holes can be changed. The lower the mass, the higher the frequency.
So what we were able to deduce, just really with a slightly more sophisticated version of what Laura's just doing really by eyeballing it, was to estimate the masses of the black holes and their distance. So we got that distance of more than 1 billion light years, 420 megaparsecs, 420 million parsecs, and a total mass of 65 solar masses, 65 times the mass of the sun.
On the 14th of...
Now, that told us that the signal we were getting was coming from a long time ago in a galaxy far, far away. And it really did feel as it was like something out of Star Wars, because the properties of the collision were quite mind-blowing. So these were 2 black holes. So again, just a cartoon representation of what was going on. You can see the dimples in space-time, a bit like our trampoline we talked about before. And then we see the 2 black holes merging. You get a burst of gravitational waves given off, represented by the red spike, just as the merger occurs, and then things settle down again. So let me run that again. All of this was unfolding over just a fraction of a second, but we could deduce information about the properties of the black holes by analysing the data. And what we got was that one of them had a mass of 29 times the mass of the sun, and the other one 36 times the mass of the sun. Add them together, that's where you get your 65 solar masses that was noted on the previous animation. But the final mass, we could estimate that as well. The final black hole, we estimated to have a mass of 62 times the mass of the sun. So where did the missing 3 solar masses go? And I remind you, that's 6 million kilograms. Well, in about a third of a second, 3 times the mass of the sun has been converted into gravitational wave energy. And remember our E equals mc squared? So that's a heck of a lot of energy released in a third of a second if it's 6 million kilograms times the speed of light squared. And if all of that is being released in just a very short time, a third of a second or so, then we can calculate what power that corresponds to, because that's energy divided by time. And it turns out to be more power, more luminosity in gravitational waves than the equivalent light power of every star in every galaxy in the entire universe, just given off in a very, very short time, and then it's gone. But nonetheless, that's a kind of a giving us a hint of just how much energy is locked up in the fabric of space-time, which gets unleashed when something as violent and dramatic as two black holes colliding occurs. So that kind of blew me away. I mean, I was involved in organising a press conference in Glasgow to accompany the one in Washington in February 2016. And the point was made in the Washington press conference as well, but I kind of went a little further, just because I'm a bit of a sci-fi fan and a Star Wars nerd. And I was emphasizing, well, I think it was Darth Vader that said no one should underestimate the power of the dark side of the universe. And that's really what that little calculation is saying, because, 50 times the light power of every star in every galaxy in the universe released in gravitational waves, but without any light being given off at all. So we really are glimpsing via our gravitational wave detectors the dark side of the universe, and there's a heck of a lot of power stored up in there. So that was our first detection. It led on to a really quite amazing period of a year or so where all kinds of celebrity events came our way. I was asked to give a talk at the National Engineering and Science Festival in Washington, where I had this sort of bizarre experience of Einstein himself. Well, yes, I know it was an actor, but Einstein coming up and asking me for my autograph. So that was quite a moment. I gave a talk at the Proms in the Albert Hall because there was a concert entitled Gravitational Waves later that 2016 in the summer of that year. And it was inspired by our discovery and written by a Dutch composer. You can even now get Gravity Wave Pale Ale in honor of the LIGO discovery. And you might, if you're in any way a fan of the Big Bang Theory, have noticed that Sheldon Cooper in an episode round about then was seen wearing the gravitational wave data on his t-shirt. There was even an episode of the game show Jeopardy where the question had the answer LIGO, the LIGO black holes. So all of this was just amazing to see how much impact it had in the public consciousness. We were on the newspapers. I think it was something like 900 newspaper front pages the day after the discovery was announced. So it was quite a ride. And in fact, the discovery was awarded the 2017 Nobel Prize in Physics to three of my senior LIGO colleagues, Rainer Weiss, Barry Barish, and Kip Thorne. And we were greatly honoured that they actually acknowledged the contributions that Glasgow had made in their presentations that they gave in Stockholm in 2017. So that was in December 2017, but earlier that same year in 2017, things had taken another dramatic turn. And that's all to do with the addition of a third detector to our network. We had the two LIGO detectors, and then Advanced Virgo, which is situated close to Pisa in Italy, joined our network for our second observing run on August 1st of 2017. And with three detectors, that enhances your capability to work out which direction the gravitational waves have come from. The way it works is this: the gravitational waves arrive at the Earth, and they won't arrive at exactly the same moment at the two LIGO detectors because they're 3,000 kilometers apart. And according to Einstein's theory, gravitational waves travel at the speed of light. We now have very good empirical evidence for that as well. And consequently, that means there's going to be a short delay between the arrival of the gravitational waves at Hanford compared with LIGO, Livingston, and vice versa. But the way it works in terms of the kind of geometry, it's really just all a bit like all that trigonometry you used to learn at high school, is that for any given two detectors, there's going to be a ring on the sky where anywhere on that ring, the arrival time of the gravitational waves coming from that direction would have the same time difference. So if you measure a time difference, you don't know where on that ring on the sky the gravitational waves actually came from. But if you've got three detectors, you can play that same mathematical game with each pair. So you've got three rings, and where the rings intersect, that's where your gravitational waves came from. So with Virgo joining the network, we had the capability to determine the sky location of our gravitational wave sources much better than we had before. So in fact, just 2 weeks later, we got our first example of this. There's the event we've just been talking about, 1509-14, the 14th of September 2015. There were two other detections that the LIGO detectors on their own had made later in 2015. But then in 2017, what we got was this event that was seen by Virgo as well. And that meant that we could localize its position in the sky to about 60 square degrees compared with between 600 or 900 square degrees for the previous ones. So that's kind of represented by those blobs on the sky. The one that was seen with Virgo as well was localized a whole lot better, 60 square degrees as shown down here. That was on the 14th of August, 2017. And we were talking about solar eclipses just before I began my talk. And I was traveling to the US for the solar eclipse on the 21st of August, 2017, when we got another spectacular discovery just 4 days previous. August 17th, what we got was not two black holes colliding this time, but two neutron stars colliding. And it was observed by the two LIGO detectors. It actually wasn't seen very strongly by Virgo at all, but we knew Virgo was operating just fine because of the other one that was seen a few days before. And there are some directions on the sky where any given detector isn't particularly sensitive. So what we knew was that this source had to be in one of Virgo's kind of blind spots, if you like, and that narrowed down its sky position quite a bit too. But most importantly, what we then got was a signal in electromagnetic radiation from the same direction in the sky and at more or less the same time. So that was a burst of gamma rays, a gamma ray burst. So what I've got now is a little animation of that. So let me play that for you. So this is the sound of the gravitational wave signal. And then just under 2 seconds later, the ping corresponds to the arrival of gamma rays detected by the Fermi satellite, also another one called Integral. And Fermi and Integral, they picked up these signals coming from the same region of sky that LIGO and Virgo had localized the gravitational waves coming from. Now, fortunately, that was a small enough region that there were only a few dozen galaxies within that patch of sky. So our colleagues with optical and other astronomical telescopes across the electromagnetic spectrum, they went looking for the aftermath of our gravitational wave signal. And they found something. They found the aftermath of the gamma ray burst in the form of an event that we refer to as a kilonova. Here's a kind of an artist's impression of it. So it's showing the aftermath of the binary neutron star pair, the neutron stars colliding together. That sends these gravitational waves out, and it also sets up a kind of chain reaction that produces the gamma ray burst. And now that takes a couple of seconds, so that's why the gamma rays arrived a few seconds after the gravitational waves. We believe that they actually set off at the same time. That's certainly what Einstein's theory predicts. And remember, this is over a very great distance. In fact, the distance we estimated to be about 140 million light years. So to only lag behind by at most 2 seconds over 140 million years tells us that the speed of gravity and the speed of light must be nigh on identical to each other. In fact, Einstein says they really should be identical to each other. And we believe that the reason the gamma rays arrived late is because they set off late, produced by the gravitational wave burst that in turn triggered the gamma ray burst. And then as the event unfolded over a number of hours, what we got was observations in the optical and the infrared, and eventually in the radio and other parts of the spectrum as well. So these observations revealed the presence of this kilonova, this remnant of the binary neutron star collision. This is a kind of before and after picture of the host galaxy, NGC 4993. Nothing very special about this galaxy, but what we see, the before Hubble telescope picture without the kilonova, and then the after just within a few hours of the gravitational wave detection. So these observations were made by telescopes all around the world, and a number of them in space. And it was, a very exciting few days. I mean, put it this way, it takes a lot for me to say that the solar eclipse in the US was only the second most exciting astronomical event that week. But nonetheless, I was trying to stay on top of the emerging, exciting picture of all this data that we had to analyse, while at the same time looking forward to the eclipse on August 21st. Now, these observations would in turn allow us to try and go back to something I mentioned near the beginning, which is to see whether we could use gravitational wave observations to measure the speed of expansion of our universe, what we call the Hubble constant, or sometimes the Hubble-Lemaitre constant. Georges Lemaitre is shown on the right there, and he was a theorist working around the same time as Hubble, and indeed Einstein, who made substantial contributions to our understanding of the Big Bang and the expanding universe that we often represent by the kind of expanding balloon analogy. Well, our ability to measure the rate at which that balloon is expanding is, even to this day, rather poor. There's a number of issues there, which I can talk about in the questions if people want to. It's often referred to as the Hubble tension, the fact that different methods for estimating that Hubble constant seem to give wildly different answers, and we don't really understand why. Well, with gravitational waves, with only one observation, we were never going to settle that. So the graph that's in the bottom right is just a way of showing you what we got from that first observation. So the green and orange vertical bands, these are measurements of that Hubble constant by different methods. And like I said a moment ago, they don't agree. And we don't really fully understand why they don't agree. And we think, well, we should be measuring the same thing. Why don't the numbers agree? But what the blue curve shows is our constraints on the Hubble constant from that first gravitational wave detection that allowed us to make that measurement. And because it's only one observation, our constraints aren't really very good. The blue curve is very broad. So, we can't really say very well at all what the Hubble constant is, but we are in the right ballpark. And that wasn't guaranteed. So, that says that we must be doing something vaguely right. And our hope has been, since 2017, that as we observe more and more gravitational wave events, then we'll be able to pin down that number, the expansion rate of the universe, the Hubble constant, better and better. So in the final bit of my talk, I want to say a bit about that, what's happened since and what's going to happen next. So jumping forward to December 2018, by that time, we'd acquired 11 gravitational wave events that we detected, the binary neutron star that we've just been discussing, plus 10 collisions of black holes. So we published a catalogue of those, and we were already, therefore, moving to a very familiar territory for many areas of astronomy, where we're interested not just in the properties of individual objects, but what we can learn from putting them all together, from making a catalogue. So our first catalogue was December 2018. And then we stopped operating the detectors for a bit longer to try to upgrade them again. So we were ready to resume operations on April 1st, 2019, and that was our third observing run. And we had high hopes that by improving the sensitivity of the detectors yet more, that we would detect a lot of events. And that's exactly how it happened. There's one of my colleagues from Hanford, Corey Gray, pointing to the clock on April 1st as our first day of the third observing run began. And one of the things we were doing differently then was we were putting out public alerts about candidate gravitational wave events right away, so that people could follow along on the internet, or they could use our app called Chirp to get updates and alerts on their phone. And in fact, in principle, since we were putting out sky maps of where the events were likely located, if somebody had a telescope, they could go look themselves and see whether they spotted a kilonova. Now, of course, the chances are you'd need a pretty big telescope to see anything. And in fact, to this day, the only event that we have seen an electromagnetic counterpart for is that event from 2017. But we absolutely want to be looking and building that kind of infrastructure so that professional astronomers and indeed amateur astronomers can go look for possible counterparts. It was important to share the information promptly, and that's what Chirp was designed to do. So what kind of things had we seen by the end of the third observing run? That takes us up to 2020. The third run lasted about a year, from April 2019 to March 2020. We stopped a little early because of the pandemic. And by the end of that third run, the total number of events we'd accumulated was 90. So we've now got a catalogue of 90 gravitational wave events, and we'll talk about the catalogue in just a moment, but I want to just highlight one or two really kind of special events from the catalogue. So on the 21st of May 2019, we detected two very massive black holes, which were our first example of what we call an intermediate mass black hole. That means a black hole more than 100 times the mass of the sun. So the two individual black holes, when they merged together, they gave a black hole of about 150 times the mass of the sun. So what's interesting about that is that the two black holes that formed that intermediate mass black hole were so massive that it's probably not likely that they individually formed from a single star. You know, one of them formed from one star, one from another. On the contrary, what we think happened is that those two black holes might have been the result of a kind of hierarchical series of mergers, where you have like one black hole merging with another one, and then what's merged sort of merging in turn later, maybe millions of years later, maybe even billions of years later, with another black hole. So that's an important part of the story that we'd like to understand better in the future. Now, the animation I've just been running there was of another event that we detected in April 2019, which basically was two black holes of not very equal mass, one a lot more massive than the other. And what that does is gives you a much richer gravitational wave signal. It's a bit like having extra harmonics on a musical note instead of it just being a single frequency. If you've got extra harmonics, it sounds like a richer tone, and that's what we were getting from events like that one. That was 1904-12, and then there was another one from August 2019, August 14th, so exactly 2 years after the black hole event that Virgo detected that I mentioned before. This time, Virgo and the two LIGO detectors detected a pair of events where we weren't actually sure if the smaller one was a neutron star or a black hole. It was either probably the least massive black hole we detected or the most massive neutron star. We think it's most likely the former, that it was just a small black hole, but nonetheless, we weren't sure. And that itself was quite interesting because we expect to see out there examples of where black holes and neutron stars merge together. So was this our first example of that? Well, maybe not, but it was opening up a new possibility there as well. And then the one you see in the bottom right here is two neutron stars that collided, just an artist's impression of that, but it was much further away. So we didn't get lucky that time and see the gamma ray burst and all the electromagnetic radiation like we had in 2017, but it was starting to build up a picture of where the neutron stars were sitting in the midst of all of this as well. So I mentioned before, I thought this one would come up earlier. Apologies, when I was talking about hierarchical measures, this is just a cartoon to illustrate that. Two black holes merge, become this one, two other black holes merge and become this one, and then these two get it together and make an even bigger black hole. So that hierarchical merging does seem to be going on, and that has important potential implications for our understanding of how black holes have formed over the history of the universe. So these are just one or two of the highlights, but I mentioned neutron stars and black holes merging a moment ago. Let me say a bit more about those, because in early 2020, just before the end of the third run, we got two more examples where we were much more sure that they really were a black hole merging with a neutron star. That's based on the masses of the two objects, gave us much greater confidence that they were almost certainly one a black hole, the other a neutron star. But the other interesting thing about this is that when a neutron star gets kind of gobbled up by a black hole, well, that can happen in different ways. So I'm just going to run these animations and talk about them briefly. So the top one is a computer simulation of a black hole and neutron star merging. We're going to zoom in on it in a minute. You can see the gravitational wave pattern being given off. But what you should watch for is the neutron star shown in orange, and it's going to be swallowed more or less in one gulp by the black hole in just a moment. There it goes. Now, meanwhile, the lower animation is another kind of scenario where a black hole gets shredded by a neutron star. I'm sorry, I said that exactly the wrong way around. A neutron star gets shredded by a black hole. So it happens over a longer time scale, and the material of the neutron star gets kind of spread out around the black hole, sort of spewing its guts, if you like, a rather unpleasant prospect getting torn apart by a black hole. So The two events that we saw in 2020 are much more likely to be the first case where the neutron star got swallowed whole, because we didn't see any accompanying electromagnetic radiation the way that you would expect if the neutron star gets torn apart in a more kind of painstaking and slow process. So the way I've liked to talk about this in schools talks or in public talks is to emphasize that that means thus far it looks like black hole neutron star pairs behave rather more like Cookie Monster, and rather more like Pac-Man than Cookie Monster. So Cookie Monster is renowned as a rather messy eater, whereas Pac-Man would gobble up the little energy pills in one gulp. And it seems to be more like that, which is going on in the two events that we've observed to date. Two neutron star black hole mergers that we've observed so far. So I mentioned the catalogue. Just about 2 years ago is when we published that catalogue, 90 gravitational wave events so far, and there's lots of resources on our website. You can look up about that, animations and some nice posters and things. But as I said, let me emphasize that we're now moving to this phase where we're just as interested in getting information from the catalogue as a whole rather than from individual events. What does it tell us about the overall picture of how gravitational wave objects are sort of forming and what kind of signals they produce, whether they be black holes or neutron stars? So I'm nearly done. I just want to bring you a bit more up to date. Let me skip that one. It's a wee bit technical. I'll be happy to go back to it if people want, but just to save time, let me just skip ahead to my final few slides. Yeah, here we are. I'm conscious of taking longer maybe than I thought I would, and I want to leave lots of time for questions. So let me just say that our fourth observing run, that began on May the 24th of this year, and it's running for about 20 months. And over the course of those 20 months, we're anticipating about 2 or 3 times increase in the event rate. So by the end of the fourth run, we would anticipate having, you know, many hundreds of events, maybe 300 or 400 overall. And thus far, there are many, many candidates that we're working with. We're analysing them, so we can't say for sure which ones are real, which ones aren't yet, but we've been sharing the candidate event properties via Chirp and via Twitter. And again, people are very interested to follow along as to how it's all unfolding. So let me just note what's coming up in the next few years to end. So that's where we are with Virgo and LIGO, but there's also a Kagra detector in Japan, which will come online a bit later in 2004. And there's also later this decade plans to operate another LIGO detector, this time in India. And the more spread across the world they are, the better we can do at localizing which direction on the sky the gravitational waves came from. So the more detectors we have, the better we can do that. But the construction of the LIGO India detector was formally confirmed earlier this year, but we've been working hard on that for a number of years. I was in India just before the pandemic, in fact, involved in some workshops about the LIGO India project, and again, much enthusiasm to do it, and it really will be potentially a game changer in giving us coverage of our detectors across the world. If you want to find out more about what we're up to, then you can go to our main LIGO.org webpage. There's lots of good resources there. We publish a magazine twice a year. You might find that interesting. The articles in that are not too technical. They're designed for a general audience. And there's even some data analysis tools. You can have a go at analysing some of the data for yourself if you want. There's some tutorials to guide you through how to do that. But let me just end by saying a few words about what comes a bit later in the 2030s. So with the ground-based detectors we have right now, like LIGO and Virgo and Kagra, there's a limit to how far out into the universe we can see. We can characterize that in terms of what we call the redshift of the sources we're observing. We can probably get out to a bit beyond redshift 1, but not too much further. But there's a project proposed in early stages, but rapidly developing stages of planning, called the Einstein telescope. It's a 3rd generation detector. First generation was LIGO, then you had advanced LIGO as 2nd generation. Next thing is the Einstein telescope. And it's going to be sited in Europe. We're still not sure exactly where. It's going to be much bigger than LIGO. It's going to be underground, which helps with making it more sensitive. And basically, the Einstein telescope and its US counterpart, called Cosmic Explorer, will really push the limits so that we're detecting pretty much every black hole binary merger in the universe. You know, we're seeing them all the way out to when they began, you know, because prior to that, there weren't any stars, there weren't any mergers because the universe wasn't old enough for the stars to exist for such mergers to occur. So that's coming in maybe about 10 to 15 years. So I'm very excited by that. And then the other area of the gravitational wave spectrum that we're looking to open up on that kind of timescale is this region here, spaceborne detectors. So these are gravitational wave signals with somewhat lower frequencies, which we would be able to detect with a spaceborne detector. There's plans for one to be led by the European Space Agency, working with NASA, called LISA, Laser Interferometer Space Antenna. And we hope that that will fly round about the mid-2030s, maybe even a little before. And then there was also announced just a couple of months ago a discovery using radio telescopes from a project called NanoGrav, North American nanohertz frequencies. So that's even lower frequencies. So just like you have an electromagnetic spectrum, there's a gravitational wave spectrum. And what ideally we want to do is to be able to detect gravitational waves all across that spectrum. So we've made detections at the high end so far, and over the next decade, we hope to extend that to the kind of middle range of frequencies. And just recently, there was the claim of a detection using nanohertz frequencies from radio telescopes from our colleagues in the US. So it's very much a lively and rapidly evolving field. And I hope I've given you a sense, not least because of what lies ahead, things like this spaceborne project called LISA that I mentioned, that, well, hopefully I've convinced you that while it's a relatively young field, it's got a very bright future. So thank you very much.
Well, that was absolutely fabulous.
I'll maybe stop you now so I can see everybody.
Oh my God, my brain's gone.
I know the feeling. As I say, I hope it wasn't too rapid a sort of race through a very exciting field, but I'm just really designed to give you a bit of an overview, and I hope I've done that. So delighted to answer any questions people have.
Yeah, well, anybody want to kick off? I mean, I'll start off with a quick one. Again, thinking about waves, is there the equivalent of a polarization of gravity?
There is indeed. I'm really glad you asked that. It's very hard to measure, but the more detectors you have, then the better chance you have to measure it, because the detectors are on different bits of the Earth. And of course, well, I hope everyone here believes that the Earth is round, but don't have any flat earthers in your midst. So that means that the detectors are oriented differently with respect to the incoming signal. And that gives you sensitivity to the polarizations of the gravitational wave. So yeah, great question. We hope to do that much better in the future, but already we can constrain the polarizations a little bit. And you know, it will get better the more detectors we have.
Yeah, yeah. And does it help if you then have detectors, because they're all sort of, I wouldn't say on the equator, but they're sort of close on. Would it be good if you had one on like the northern latitude or the southern latitude?
It
like,
absolutely would.
Africa,
I mean, the back history of this is quite interesting. Back in the mid-2000s, before we'd even detected anything, the Australian government got really interested in having a detector there. Now that's come back. There's another smaller detector that the Australian government are hoping to build. But in the meantime, because of the kind of the big crash in 2008, the Australian government kind of chickened out. I mean, clearly what also didn't help was that we hadn't actually detected anything yet, you know? So it was a bit hard to convince governments to build these things, you know, when it was still as yet unproven technology. But in between, and not least because we did make the detections, that convinced India to throw their hat in the ring. But ideally, you know, if India could be moved to the southern hemisphere, that would be better, because it would give you that better coverage. I had a student some years ago, and we did a kind of a study to try and work out, you know, where's the best place on Earth to maximize your sensitivity to the polarization, to the sky position and all of that. And Australia always won that hands down. But of course, it's not just about the science, it's about the money. And that's why, you know, we've gone with LIGO India in the meantime.
And I guess you'd rule out New Zealand because it's just too wobbly, too many volcanoes. And
not necessarily. I mean, it's a good point, but actually, for that matter, Pisa and, you know, Tuscany is not that great. And Kagra in Japan, you know, they've got lots of seismic disturbances. The key thing is that those seismic disturbances are all at much lower frequencies. So it's easy to screen them out. But I noticed Martin had posed a question in the chat, and that maybe gives me a kind of a neat segue into your question, Martin, because the Einstein telescope does push a little bit to low frequencies to about 1 hertz. And that's why we're going to put it underground, because it's a little bit easier to sort of mitigate the impact of those seismic disturbances if you're already underground. But if you really want to go to much lower frequencies than that, then you're totally stuffed, because the Earth just shakes too much. And that's where, you know, as you say, you know, certain locations in the Earth shake a lot. So going into space opens up the sort of like millihertz range, you know, thousands of a hertz. And what that gives you is the chance to detect much more massive black holes than you would be able to detect from the ground. So we're seeing black holes which are, you know, tens or even hundreds of times the mass of the sun. But we believe from indirect evidence that pretty much every galaxy has got a supermassive black hole at the center. Now, if two galaxies merged, and we think a lot of that happened in the past, you see images from Webb and from Hubble showing mergers of galaxies. We see that in light. But if those black holes at the center of those galaxies also merge, then LISA will detect the gravitational waves from them. So that will help us to understand a bit better how galaxies formed and the role that black holes played in amidst all of that. But these are those supermassive black holes. You know, you maybe have heard of like Cygnus X1, which is the one that we think is at the center of our own galaxy. There was that amazing picture from the Event Horizon telescope that imaged the light around it. Well, what, you know, gravitational waves would do is give us a chance to actually kind of image the gravitational waves coming from the black holes themselves.
Fantastic. Well, any other questions? I might still spin.
Just one, if I might. I was interested in the comments you were saying, I think earlier in the talk, about the Hubble tension.
Yeah.
And I was, you then wanted to say that there's more information as the catalogues got bigger. I was wondering if there was any conclusions when you got.
Well, no conclusion yet, but things have improved. So again, I suspected someone might want to ask about that. So rather than delay kind of finishing my talk, if you'll allow me just to go back now and share a couple of slides, I'll be happy to answer that question. So let me share again. And it was towards the end. I just had them in as kind of bonus content in case anyone asked about that. This is something we've been working hard on in Glasgow. So I'll skip some of the gory details that are a bit technical. But essentially, what it comes down to is this. If it's two black holes merging, then you don't really know which galaxy that's happening in, because you don't get any light given off. You don't see a gamma ray burst that would tell you, you know, pinpoint the location. But it's not that bad, because with multiple detectors, you can localize the sky position pretty well. So this is the one that actually we did nail down the galaxy very precisely because of the gamma ray burst, NGC 4993. But, you know, the sky localization was only about 30 square degrees. So there was a few dozen galaxies in that area. Now, if it's a black hole merger, therefore, what you need to then have kind of usable information to help you get the Hubble constant is you need to get the redshift, or the recession velocity of the source. So you don't get that from the gravitational waves. You would get that by knowing what the redshift of the host galaxy is. You get the distance from the gravitational waves, and then you put those two together. So the problem is you don't know which is the true host galaxy. So what you do is you treat all galaxies within where you know the gravitational waves are coming from as potential host galaxies, and then like average over them, or the technical term is marginalize over them in terms of how you do. This is all done in the framework of what's called Bayesian inference. Sorry, just let me kill that. So let me skip this one because it's a wee bit technical and just go to this. So this is the kind of the bottom line. Sorry, again, it's still, you know, quite detailed graphs, but let me just walk you through it. So the one on the left shows two things. It first of all shows the orange curve, which is the one I showed before. So I've changed the color scheme for no particular reason. Sorry, that's a bit annoying. But the two colored vertical bands are ways of getting the Hubble constant by traditional electromagnetic means that don't agree with each other. So that's basically your Hubble tension, the fact that the purple band and the green band don't overlap. So our single observation was pretty broad And therefore, it didn't really resolve that. It was kind of tempting to say, well, it looks like it agrees with the purple one, the lower value better. But actually, the breadth is such that you can't really say that yet. But then by 2018, we'd observed a total of 11 sources, 10 of them black hole mergers. So we didn't know for sure what their redshift was, but we could do this averaging trick of averaging over all the potential host galaxies. And that gave us, when we combine with the neutron star merger from 2017, the blue curve. So we're sharpening up a little bit, you know, our inference is getting better. Still not really enough to favor the purple over the green, but it does seem to be homing in the purple a bit more. And if you fast forward to the right-hand plot, this is our most recent results to date. So it's still a little old. We published these first 2 years ago, and then that was on what we call the archive. You probably know about that. It's a preprint server, and then it got refereed, of course, and you know that was a few months later, but the results didn't really change. After peer review, they still look like this. So again, forgive me for having changed the color scheme because they're from different papers. The black one is that original 2017 result, very broad, not very precise. And then what we're getting now from a total of 47 events, so up from 1 to 11 to now 47, well, it does still seem to be homing in on that lower value of the Hubble constant. So it's not really precise enough yet for me to, you know, nail my colours to the mast and say I think the lower Hubble constant is the correct one, but we're getting there. And I think what we'll probably need is about 200 or so before we can really start to make a, you know, definitive claim. And I reckon by the end of our 4th observing run, or maybe somewhere in our 5th run, which will be about 2026 or thereabouts, then we might be able to say. So I know that's a while to wait, but hey, the universe has been around for 14 billion years. We can wait a couple years more to settle this Hubble tension question. Would we truly settle it? Well, I don't know. You know, there could be problems with our data as well, but I've worked in this field really all my career, and it's so perplexing that these, you know, purple and green results don't agree. We just don't know what's going on. It's maybe got something to do with a misunderstanding of dark energy and the properties of that. So if the gravitational waves can bring any fresh insight to help us answer those questions, you know, the community is really hopeful that that might happen. So that's going to keep me busy for the next few years.
Thank you, Martin. Thank you very much. Really interesting.
I've got a question about, do we have an idea of how many potential events there could be that generate gravitational waves, and what percentage do you think that we're actually observing currently in that spectrum?
We do indeed. In fact, I maybe won't share the slides again because the graphs aren't particularly illuminating, but one of the other graphs I had in that presentation from another version of this talk I'd done recently in a university setting is presenting our analysis of exactly that. So there's a few things to say. Firstly, it was a source of considerable interest to us that we got a detection just a few days after the advanced LIGO upgrades had taken place. So straight away that led us to think, well, geez, if there's that many events out there, why weren't we seeing these before? Now, in a sense, that's quite an interesting story. You know, we all have to do our bit to talk up Britain. So let me do that now, because the UK's contribution to the advanced LIGO upgrades was improving the sensitivity by having those silica fibers instead of steel fibers. And what that did was gave us better sensitivity at lower frequencies. So not as low as LISA will do, but a little bit lower than before. And if you remember from that animation that my colleague Laura was narrating, then heavier black holes will tend to give off signals at somewhat lower frequencies. So consequently, what that led us to realize was that, yeah, there's a lot of black holes out there. Many of them are a bit heavier than we thought maybe were likely. And that's why we weren't seeing them. Well, it's part of why we weren't seeing them before with LIGO. It wasn't just that LIGO wasn't kind of sensitive enough. It was sensitive in the wrong frequency range. So that reassured us that actually it wasn't that strange that we detected something so quickly after advanced LIGO switched on. It was like someone that had been, you know, like death unable to hear before suddenly getting a hearing aid. You know, you wouldn't be surprised to suddenly start hearing traffic noise, and you know, all of that was there before, you just couldn't hear it. And then what it allowed us immediately then to do was to begin estimating how many events there are out there. So from the first few detections, you can't really do that terribly well, but the more detections you have, the more confident you can be that your inference about what the total population is more robust. It's a bit like, you know, the principles you use for opinion polls. If you only sample the opinion of 5 people, it's not very reliable. If you do a few thousand, then it starts to get more of an indication of what the, you know, the national picture is. So in those terms, we think that there's basically a black hole merger happening somewhere in the universe about every 15 minutes. But we're now at a stage where we're getting a candidate detection about once a day, once every day and a half. So as you can see, there's still a lot that we're not seeing. And that's why the Einstein telescope will help to improve further, because it will see much further out. We won't miss them because they're too faint. We can infer that they must be there from the ones we see, but we'd like to detect them as well. And that's what will happen next decade with the Einstein telescope.
Thank you.
So sorry, it was a rather long answer, but it's a really good question that deserved, you know, an in-depth reply. I hope that was helping. Martin is saying, if frequency reduces with massive black holes, how does this work with redshift reducing frequency? Well, an excellent question as well. What we observe is the redshifted mass. Well, what I mean by that is it's the actual mass multiplied by 1 plus the redshift. So just as light is shifted, gravitational waves are stretched as well. Now, in the case of light, we can correct for that galaxy by galaxy by looking for features in the spectrum that we understand on a theoretical level, like, you know, a hydrogen line. We know what its frequency should be, we observe what it is, and therefore we get the redshift. That's hard to do with gravitational waves. There isn't an equivalent sort of line spectrum of spectral lines for gravitational waves. Well, there's actually been a few suggestions of things we might look for, but nothing as obviously useful as like the atomic line transitions that we use in astronomy from, say, the hydrogen atom. So that's why, to get the Hubble constant from gravitational waves, we get the distance from the gravitational waves. But if we want to get the redshift, we need the host galaxy. So that not only tells us the redshift, but it also tells us what the true mass is, because we can then correct for the redshifting of the mass and what we observe. So it's just essentially all thrown into our analysis. That's why we've got to be very good at data analysis. All of these problems involve, you know, high performance computing. A lot of computing power has to be thrown at it. We're beginning to look at using AI for that. You know, I've got a paper with a colleague and one of our students that we just put on the archive a few days ago that's looking at using machine learning approaches to try and kind of learn better the relationship between what we see and what's truly out there. So the field will continue to evolve, not just in terms of the hardware, but the software as well.
One of your slides indicated the different frequencies that you can observe based, I think you had one land-based, moving up to space-based, etc., etc. Are those different frequencies, they generated by different types of events or different?
Excellent question as well.
Different distances away.
A combination of both, frankly. So maybe this one is worth just sharing again, because a very good question. Let me just do that. Take a moment to do that. So just maximize the screen. Here we are. Right. So I'd spent so little time in this slide that I didn't get the chance to address the question you've just asked. So it's a very good one. For almost all of my talk, I was focusing on compact mergers, compact binary systems where they coalesce together, whether it be black holes or neutron stars, or indeed supermassive black holes, which is just a scaled up version of the kind of black holes that LIGO sees. But there are other possibilities too, and they give quite different types of signal. There's the possibility, even with ground-based telescopes, to see gravitational waves from a single isolated neutron star that's spinning and isn't perfectly round, but has got a kind of bump in its surface, and that will introduce a wobble in space-time because of the wobble in the neutron star itself. So we haven't detected that, but things like the neutron star at the heart of the Crab Nebula, which was detected by Jocelyn Bell back in 1967, we've been searching for gravitational waves from that, and because we haven't detected any yet, that allows us to say how round that neutron star must be. It can't be any less round than such and such, otherwise we would have seen the bumps already. So it's kind of basically about the most round thing we've found in the universe, you know, like way rounder than a billiard ball or anything like that. You know, the bumps can be no higher than about 1 part in 100 million or thereabouts. So, you know, if it's about 10 kilometers across, you're talking, you know, centimeters or even less. So that's the stage we're at, but it would be great if we could actually detect those signals, because what they would also tell us is a little bit about what the neutron star is made of. The stronger the crust of the neutron star is, then the more readily it's able to support being a little bit egg-shaped without kind of tearing itself apart. So this would give us a way to do, if you like, seismography inside neutron stars, which would be pretty cool, but we haven't been able to do that yet. And then the other type of source to mention is maybe the most kind of exotic of all, which is radiation, gravitational radiation, left over from the Big Bang itself. And in there lies a little bit of a cautionary tale, because in 2014, there was a report from a mission project at the South Pole called BICEP-2 that they claim to have detected this. Not directly, not gravitational waves directly the way that we do with LIGO, but kind of gravitational waves imprinted on what we call the cosmic background radiation. You know, you've probably had talks about that before or know lots about that. So specifically, this takes me back to your first question, Keith. Gravitational waves of different polarizations would produce a pattern in the cosmic background radiation that would also be seen in its polarization. So BICEP-2 claimed to have detected that, and you know, everybody got very excited, but then a few months later they said, actually, we're not so sure. It might just have been dust from our galaxy sort of imprinting a polarization signal rather than from the Big Bang. So that's another kind of big frontier, is to detect gravitational waves from the Big Bang. Now, those wouldn't be from black holes. Well, actually, they could be. They could be from things called primordial black holes that are so tiny that they're kind of tucked away just soon after the Big Bang. But they could also be from exotic things like cosmic strings or textures or membranes, you know, also kind of exotic theories beyond Einstein's theory of gravity that would predict these. So one of these days it would be great to probe that as well, but that's going to take longer because the stretching of the gravitational waves by the redshifting as the universe has expanded, what that does is it shifts the signals to much, much lower frequencies. And that means that really our only prospect for the immediate future of seeing all this kind of stuff is imprinted on the CMBR. LIGO's not going to see signals from the Big Bang. I mean, you know, we look for them, but not with any great hope of seeing them, because they ought to be so weak and at such low frequencies that only the CMBR would be our means of detecting them. So again, sorry, that was a rather long answer, but a really pertinent question.
Thank you.
Any other questions? I've got another quick one. You're saying there, Martin, about I can understand on neutron star if it's got lumps, but I believe neutron stars also have like neutron quakes. So whether
yes, absolutely, yeah.
So would they create a gravity wave then?
If they were strong enough, if they were powerful enough, they would. These things are difficult to detect anyway. So the advantage of it being a lump that's kind of sitting there for a long time is that you can build up the signal over years. Whereas if it's a quake, then, you know, let me say a bit more what I mean by that. When I say you build up a signal over years, what you're looking for is like, you know, a small wobble that repeats over and over again. And if you kind of fold the signal, you know, you can do this with sound waves as well, then you would eventually kind of pick that.
There's right in it.
Noise. Pardon me?
So I think it's just a bit of interference. Don't worry.
Bit of background noise, quite appropriate in the context. But if it's a quake, then it's over and done with in a very short time. So it would have to be quite a strong one to kind of show up in our data. Because a lot of the I don't know if this is, you know, outside anyone's experience, but if the words Fourier series mean anything to you, or if they bring back nightmares from a former life, fair enough. But essentially, a lot of our analysis is done in Fourier space, and that means if it's like a very localized in time event, then actually it's quite hard to pick that up in Fourier space.
Yeah, that gave me a few nightmares, so stop that, Martin.
Indeed, I won't go any further. Yeah. Trigger words, yeah. I'm afraid this is what I have to spend my time doing. But yeah, I'm delighted to have had the chance to talk to you all. I mean, you know, if there are more questions, I'm happy to answer. I should mention I've actually got a telecon to attend in about half an hour. So
no, that's fine. No, you've done
some dinner in between, but
I'd just like to quickly say for everybody, everybody wants to give a reaction to Martin's absolutely staggering talk. Certainly from me.
Well,
thank you very much.
much.
And as I say, we'll be putting that up on our website, so anybody else who didn't catch it tonight can catch up later. But that's been fabulous, Martin. Yeah, I think I've got a few questions I'll be pinging back to you later on.
Please do. Happy to answer them. Absolutely. And it's been a real pleasure.
Yeah, and I think we'll have to plan a follow-up session when you're sort of, I mean, maybe not waiting for the Einstein observatory, because that's a few years away.
Yeah, sure. Can do something a bit sooner than
the
that.
data analysis you're doing from the more and more results, you're going to come with a whole zoo of information that's going to be analysed, and be fascinating to see what that says.
Good stuff. Right, all the best, everyone. Take care.
Thanks, Martin.
Thank you. Thank you.
Bye-bye.
Thank you.